Now we're going to look at the next section, and this is about continuity. The base word for continuity is continuous, and when we refer to a curve being continuous, that means it doesn't have any holes or breaks. You can draw it with your pen on the paper, never having to lift it up off of the paper. So a function is continuous over an interval if its graph over the interval can be drawn without removing pen from the paper. A function whose graph is broken, disconnected at x equals a, is said to be discontinuous at x equals a. So the definition of continuity: a function f is continuous at the point x equals a if all of the following are true. The limit of the function as x approaches a has to exist. The functional value at a has to exist. And the third one here is number 1 and number 2 have to be equal. So we'll be looking at some problems and see what happens or what part of this definition breaks down. First thing, part A, we got to determine where each function is continuous. If you remember how to find domain, then you can also tell me at the same time where the function is continuous, because you're telling me about the usable x values. In my first function, g of x, if you'll notice, I do not have any denominators, I have no radicals. Actually, in this particular function, I can use all real numbers, so negative infinity to positive infinity. In the next one, I do have issues. Notice I've got a fraction bar. I cannot use x equals negative 3. So you could tell me it's continuous for all x except negative 3. You could say it's continuous for negative infinity, comma, negative 3 in parentheses, union, another pair of parentheses, negative 3 to infinity, which says the exact same thing as I did before. In the third one, see if you can determine where it will be continuous at, and stop me for a second, you go find it. Now, for me, this thing is continuous for all x except 0 and negative 7. If you'll notice, you need to factor the denominator, and factoring the denominator, setting those factors individually equal to 0, will tell me where x is equal to 0, or where my denominator is equal to 0, and I can't have that. So you are excluding anything that leads to division by 0. Now part B, I've got myself a function here. For problems 1 through 6, which we'll find out here in just a second, we need to refer to the function below. Use the graph to estimate limits as outlined below. Okay, so what they want us to do is for each value of a, and if you'll notice I'm going to have 6 different values, we need to find the limit of the function as x approaches a from the left, the limit of the function as x approaches a from the right, and then from these two I'm going to see if I've got an answer here. Then we're going to have or find the functional value at a, and then we're going to see if the limit equals that functional value. So in a way, we're doing this definition. We're finding the limit, we're finding the functional value, see if they exist, and then we're going to see if they're equal to one another. So at a equals 0, so x equals 0, I'm looking right here. Notice it is solid. I have actually 3 instances on this graph where I do have issues. Notice there's a break here, here, and here. When I have breaks, I'm going to have problems with that definition above. But x equals 0 doesn't seem to be one of those. So the limit of my function as x approaches 0 from the left, it looks like it's going to be 1. Coming in from the right, it's going to be 1. So the limit of my function as x approaches 0 is going to equal 1. F of 0, if you'll notice, the actual functional value is right here at 1. Now the limit of f of x as x approaches 0 is equal to f of 0, since both of those are equal to 1. So my curve is continuous. It's because it's solid at that particular x value. Let's see, at a equals -1. Well, if we look at -1, an x value of -1, notice it is also solid. But let's go ahead and find out these answers. The limit of my function as x approaches a, or in this case -1 from the left, looks like 0. From the right, it is 0. So the limit of the function as x approaches -1, this is 0. F of -1 is 0. And they do equal one another, so the curve is continuous. How about when a is equal to 1? Notice this is one of those problems where I do have an issue. So limit of my function as x approaches 1 from the left, it looks like it's going to a y value of 2. Coming in from the right, it looks like I'm approaching a y value of 1. So the limit here does not exist. So there's really no reason for me to get the rest of the values because this function is not continuous. Now from my graph, if I tried to find f of 1, it looks like I'd have to go with maybe 2, but this really is looking at something being continuous, and it's not because I do have a break. And it falls apart at the very first one where I've got a limit. I don't. What about if x is equal to 2? Here's another issue. Let's see what happens. The limit of my function as x approaches 2 from the left, it looks like I'm approaching a y value of 2. From the right, it looks like I'm approaching a y value of 2. So my limit of my function as x approaches 2 is equal to 2. Now f of 2 does not exist. So the limit does not equal the functional value, so it is not continuous. Like I said, we can see that, but you've got to know which one of these pieces falls through. So in this particular case, in problem number 4, I do not have a functional value. What about when a is equal to -2? Remember, this is my other issue on this graph. So the limit of this function as x approaches -2 from the left looks like I'm getting close to a y value of 1. From the right, it looks like I get close to a y value of 1. So the limit of my function as x approaches -2 is equal to 1. So remember that. F of -2, do you see the solid dot? Well, f of -2 equals 3. So this value is equal to 3. Does the limit equal the functional value? No. This was 1, this was 3, so my function is not continuous at an x value of -2. What about 0.5? So here's a half. 0.5 is about right here. It is solid, so I should have my functional value, my limit, they should all be equal. It looks like they're going to equal, what, about 1.5? And it is solid, so I know it's continuous. So this is pretty much what you need to do on your homework. There'll be problems like these where you have to tell where the function is continuous. So remember your domain work because it will come into play here. This part, they do this. They get you going one piece at a time to see if you can satisfy the definition above. Last part on continuity. A polynomial function is continuous for all real x. If it's a polynomial, my domain is -infinity to +infinity, or all real numbers. A rational function is continuous for all real x except those values of x where the denominator is 0. So in this part A, my k of x and my capital F of x are good instances or examples of that particular problem. An exponential function is continuous for all real x. Say y equals 2 to the x. If you graph that, you'll see it comes in from the left and goes out on your right. Natural logarithm function is continuous for all real x in its domain. Remember, the domain of a natural log is has to be greater than 0. A radical function or rational exponent function is continuous for all real x in its domain. So guys, the domain plays a big role in continuity. If you can tell me domain, you can tell me where the function is continuous at. So that's all for this particular part of this section. I'll pick up the next part in my next video. Thank you.